Good day, my name is Ismael Aragorn Inocencio, and I will be presenting the multi-criteria ratings methodology for the suitability evaluation of open pier sites. I would also like to acknowledge my co-authors, Eric C. Cruz and Edgardo P. Casilar II. All three of us work for AMH Philippines Incorporated, a Filipino engineering consultancy firm, while Eric C. Cruz is also a professor at the University of the Philippines, Diliman. So for a quick outline, I will be discussing the background, objectives, the marine trestle length, the prevailing wave maps, soffit elevation and design wave height, the final pier siting suitability matrix, and finally the conclusions. So for a quick background, an open pier for cargo is to be optimally sited along a 6-kilometer long coastline, which is partially sheltered against waves. Several reaches of the coastline are dotted with fully grown mangroves, while some are close to channel outfalls and debris stagnation zones. However, local laws do not allow for clearing of mangroves. As such, while the siting is mainly governed by the requirement of wave tranquility, other coastal engineering and operational considerations are important to the project owners. 5 potential areas with sufficient space and clearance from mangroves were determined. Selecting an objective ratings-based approach was implemented to determine the optimal location based on coastal engineering and non-coastal considerations. Presented here are the first 3 coastal engineering considerations. First is the marine trestle length, which is primarily a function of the vessel draft requirement. Second is the maximum vertical distance to seabed, which is the depth of the marine pile from the mean tide level to the seabed elevation as a result of the landing alignment. Third is the soffit elevation requirement, which is the minimum elevation of the deck soffit, or the bottom of the deck, based on the sum of the freeboard and the highest combined wave run-up and storm tide level from the simulated critical typhoons. Fourth is the design wave height, which is simply the highest significant wave height calculated from the critical typhoons and will be used for the sizing and design of the marine piles. Fourth is the dredging requirement, which is the approximate area that will have to be dredged as a result of the pier alignment and the turning basin of the vessel. Last is the landing alignment, which is ideally on the direction of the prevailing wave approach, or wave optimal, to reduce the size of the marine piles, but could sometimes be not aligned with the wave approach to compensate with the pile depth due to bathymetry. So first, the considerations for the marine trestle length. The designed vessel is a Panamax-like vessel with a depth of 12.04 meters. This results in an under-keel clearance of 1.2 meters, and with a tidal variation from mean tide level and mean lower low of 0.57, we determined that the required draft is roughly 13.81 meters from mean tide level. For the turning radius, it was determined a 590-meter diameter turning basin would be required for a vessel with a low of 295 meters. So for the marine trestle length of Site 1A, the trestle would have to be 490 meters long to reach the approximate -14 meter depth requirement for the draft. Assuming a wave optimal approach, which will be discussed later, the bursting area can be tilted along this degree. However, it should be noted, because of this approach, the pile length would have to reach roughly 25 meters depth. As an alternative, we have what we call the depth optimal alignment, where the berthing area is parallel to the 14-meter contour. However, because of this alignment, there is a potential navigational hazard that was determined during the bathymetric survey that can be potentially shallower than the 14 meters. So this is another sample for the second site, site 2B, depth optimal, where although the 14-meter depth requirement is met, there are small potential navigational hazards which have to be verified or dredged. These are just additional samples for site 3, where we have a relatively shorter trestle at 385, and site 4 with actually the shortest trestle length of only 215 meters because of the change in bathymetry. Site 5, we have roughly the same length of 240 meters. We also analyzed the prevailing wave conditions of all sites based on the windrows and available fetch for each location. So this is a sample for the first site where we have the wave optimal approach such that the prevailing wave coming from the south runs parallel to the proposed pier alignment. Or the depth optimal, wherein the refraction of the waves will now be hitting transversely across the vessel, inducing more load transfer to the fenders and pier. Now for a quick discussion on the soft elevation and design wave height. To determine the potentially critical typhoons, a 200-kilometer search radius was placed around the project location, after which 7 potentially critical typhoons were selected based on their wind velocity, pressure, and distance to the site. To help illustrate the terminology, the minimum soffit elevation is a summary of the storm wave, the storm surge, and the astronomic tide. This is to ensure that the open deck pier will not be inundated by waves which would induce wave and deck forces and may damage any potential infrastructure located on top of the pier. For the typhoon simulation, a regional mesh including all of the Philippines extending into the Pacific Ocean and West Philippine Sea was created. Simulations were done using Mike 21 by DHI. Also not shown here is a local mesh specifically made for the project site. So these are just sample results for Site 1A for the different typhoons that pass within the area. We can see here there's a potential maximum storm tide and wave run-up and the corresponding storm tide. The idea being that the maximum storm tide and the maximum wave height do not coincide. So this just shows some additional sample results for Site 2A, where the exposure is slightly different. To summarize all sites, we found that the 1987 Typhoon Betty, or local name Herming, produced the highest soffit elevation requirement, ranging from 5.1 to 5.4 depending on the location. Now all of this was input into the previously discussed pier siting suitability matrix. Each pier alignment was rated from 1 to 10 based on the suitability to the corresponding criterion, with 1 being the most suitable. Weights are given to each parameter based on the consultant's engineering judgment. A higher weight signifies a more critical factor for siting. One matrix was created for coastal engineering considerations, while another for operational or non-coastal engineering considerations. So to illustrate, a higher value of the marine trestle length indicates a longer trestle, which would result in a higher capex for the proponent. Conversely, a lower value is more advantageous as it would result in a shorter trestle. So similar high and low versus disadvantageous and advantageous assessments were made for all parameters. To illustrate, item A, or the marine trestle length, is the length from the shoreline to the pier landing or the berthing area. Items B, C, E, and F correspond to the piles in their respective locations. So to summarize the characteristics of the different sites based on the 6 considerations, these are the final data per site per parameter. For example, we can see here the shortest trestle length is at site 4 at 215 meters, with the longest at site 1A and 1B. Here we have the score and the corresponding weight per site per parameter. These were based on equations set and agreed upon with the proponent. To summarize this, we've got site 5 has the lowest score, meaning it is the most optimal based on the coastal engineering considerations. However, as mentioned before, non-coastal engineering considerations were also taken into account. Specifically, the inland topography, proximity to existing roads, area for port development, and other concerns. Similarly to the coastal engineering considerations, higher or lower values were ascertained depending on whether it was advantageous or disadvantageous. These are the data, which again, based on an equation, scores were applied. Specifically, these are the scores and weights applied per site per parameter for the non-coastal engineering considerations. Summarizing the operational considerations, it was determined that site 3 is actually the most optimal. However, combining the scores, we find that it is actually site 4 which is the most optimal in terms of coastal and non-coastal engineering considerations. Conclusions. The multi-criteria ratings with generally objective weighting factors identified a clear optimal pier site based on both technical and operational considerations. The application of such a multi-criteria decision matrix may be applied to future shorelines to ensure the most technically feasible and potentially economically viable location for pier development to be chosen. As it is a multi-criteria approach, criteria may be added or removed as needed, depending on the characteristics of the site and the requirements of the proponent. Special acknowledgements. The authors would like to recognize the assistance provided by engineer Ben Jetro Evangelista for his assistance in the preparation of the original figures and calculations presented herein. Thank you.